Our next speaker is Svet Hristozkov. Apologies if I got that wrong, Svet, from Graphcore. He's a verification engineer, and he's going to talk about coverage in Python, the pros and cons. Svet started his career at CERN in 2014, where he stayed until 2017 working on the LPD pixel sensor chip for the LHC upgrade. For the past 4 years, he's been part of the verification team working on the IPU at Graphcore. Over to you, Svet.
Thank you, Mike. Hello. Like you heard, my name is Svet. Been at Graphcore for the past 4 years, and I'll just give you a brief talk. I should have spent a little more time coming up with a smarter title, but there we are. Right, so what do we typically do in verification, and where does coverage fit in? So ordinarily, we have a process that looks something like what I've got here on the picture on the left-hand side. We've got a verification plan, and we've got some regression tests, a set of test suites, a set of scenarios that we run. We collect some metrics on them, and we map them onto our verification plan, and hopefully, at the end of the day, we've hit our coverage goals, and we can take back the chip. So where's the problem with this? We've got multiple places to change. So firstly, we have to define a verification plan. That could be text, XML, anything really. I imagine that's very team specific. We have to collect coverage. Typically, that would be in some way incorporating SVE coverage. And we then have to use typically a vendor-specific tool to put it all together and produce a report that we can view and review and work on and iterate over that process. So there's multiple things going on here, like that picture there's trying to show. And that is all before architecture rains on our parade again and changes the specification, and we have to go over that process again. So how can we use Python here to improve our productivity? So we're just looking to improve our productivity in this entire flow, and the reason we've chosen Python to do that is because it's really expressive. There's loads of support on the internet, a very vibrant community, and it's very easy to interface with loads of different things. So let's see how we can streamline that loop. So if we have so we start from our architectural specification here. That feeds into our Python. We'll try and produce a verification plan using our Python, and then when we get back to running a simulation, here's that little waveform here signifying our simulator. We feed that via the DPI and into Python, and what we can do then is we can put that into a nice SQL database, because Python has easy integration into that. We can maybe produce some nice reports that we can even view in a web viewer. So that's roughly the plan. There's loads I can talk about here in each individual step, but let's skip that for now. So I've got a demo here, which I'll get back to at the end, and I won't go into too much detail just now because I don't have that much time. But what I've shown here is I've come up with an architecture for a protocol called Svet. What a coincidence. I've defined that protocol here using an XML description here that I specified myself. That could be an IP exact description, could be any sort of architectural specification output. So my protocol is quite simple. It's got a header. It's got 4 fields which add up to 32 bits if you see here. So called command 2 bits, address 12 bits, chip select 1 bit and reserved. And then it's also got a payload. And what I'd like to do is write some coverage for this and produce a nice verification plan and eventually a nice verification report for this. And I've just shown you here what my cover point for that looks like in Python. So as you can see, this is very brief, so not verbose at all. What I do here is I use a nice, I use XPath to iterate over all my fields in my header, and I add an axis for each field here. So that would be the equivalent of a system Verilog cover point, and doing a cross on all of those. So essentially I've got 4 cover points and I do a cross on all of them in system Verilog terms. And that will be my my cross. What I've also done is I've tried to write some text motivating why is that coverage important, when is it collected, how is it collected, what does it signify, etc., etc. And eventually I'll produce this nice report page here, which shows me some of the enumerations for my fields here, which I've taken from the XML as well. So if the XML were to change, this will change as well, and we'll be notified, and we will not have to go any maintenance on this. What's also important to point out here, I've managed to define my coverage without actually writing any coverage collection code. I can do that later on, and I'll show you in my demo how we do that, and even run a quick simulation where we collect coverage, but let's skip that for now. Let me just move on to the next slide. So why would we bother with all of this? So one of the nice benefits we get is we get simulator independence. What does that mean? It means we can run coverage in any simulator and even combine it together. So I can run my coverage in Questa, I can run it in Cadence, run it in VCS, can run it even in Verilator, I can run it offline. And at the end of the day, I can merge all of these data sources together because it's all lives in a SQL database, so it's quite easy to merge. And it also enables different workflows, like Ian and Ray alluded to before. So what I typically do, I'll typically work on my stimulus offline without the simulator, look at my coverage, tune my stimulus again, tune my constraints, for example, and only then do I go and run it on an actual simulator, which is probably going to take time looking for bugs. What I can also do is I can write some extended tools for using Python. For example, I can optimize a test set, which is to say I can select a bunch of seeds which will give me the most coverage for the least number of seeds to put in a CUI run, for example. I can write different tools that, to my knowledge, do not exist. So, for example, I can do a coverage diff. I can essentially do a diff of two regressions, see if I, for example, change the constraint and my coverage has dropped off. I can do what we call a non-congruent merge of coverage. And what that means is as soon as you change a cover point, you can no longer merge two regressions together. With this feature here, what we can do is we can essentially filter out the cover points which differ between two regressions and merge all the others together. So that allows us to reuse old data, which we judge to still be relevant, essentially reusing old seeds that we've already run to see where we are in terms of stimulus. And we can generate some nice web views, like I'll show in a second. And finally, we actually get a nice performance boost using this, almost as much as to say we get close to no penalty for running coverage. And I've just shown here two examples that I'll go into detail, which is multitrading, and we can also prune away cover points, and I'll go into some details into that as well. So let's look at those in a second before we get onto the demo. So what do I mean when I say multitrading? So typically, what happens is we have a simulation thread that runs and executes some RTL. We eventually get to some interesting events. Our monitor will collect a packet, for example, and it will then call into our coverage in system Verilog, and then the simulator under the hood will process that coverage, increment the count of how many events we've seen, and then it will revert back to the simulation. So what we can do here is we can split those two processes. So what we can do is we can have our simulation thread run up to an interesting event, send the data via DPI to our to a Python coverage processing node thread, and then we go back to our simulation thread. So the two at this point run concurrently and are independent of each other. Eventually, we'll get to another interesting event, and the whole thing repeats. So how much you gain by doing this will depend on how coverage intensive the current seed is, what you're actually doing in the simulation. But I've just shown you some real life example here. If I run one particular test that we had, if I run a single thread, it takes 320 seconds. If I run it with two threads, taking my Python processing thread offline, I get down to about 30% less. But what I've seen here is my load average. So this is how many cores I'm using. So in a single thread, I'm pretty much using 100% of my CPU time for a single core. Here, I got to 1.5. So that actually means some of the time I'm using 2 cores. So that will not actually improve my total compute time. So in terms of compute budgets, this is a zero-sum game, so it will not do anything. However, in terms of latency, if you're doing interactive coverage and interactive debug, this is a massive improvement. Another performance thing is what we call coverage pruning. So typically, I think most people would be familiar with this sort of graph. So as we have more and more tests, the number of cover points we fully hit follows a curve that looks like this. So we very rapidly hit coverage initially, and then we soon hit diminishing returns. Soon after that, hit diminishing returns. However, in terms of the number of cover points collecting, all of the cover points that are fully hit very rapidly still take time to process the information, and we essentially collect worthless data. So what we can do is we can say, okay, we'll take the cover points we hit very easily, and we'll prime our simulation with those cover points, and we'll tell the coverage collection, do not collect any coverage for those cover points only, and collect the cover points that are interesting. So what happens if I do that? So I've taken a sample regression here to prime my runs with. So this is a regression I've run ahead of time. In that regression, I've hit 45%, nearly 45% of cover points at 100%. So I'll now disable those cover points that I've hit here at 100%, and I'll see what I gain in terms of runtime. So I then run another regression, one with cover points pruned and one without, using the exact same seed. So this is running the exact same tests. What happens is the one that I've got pruning turned on, I collect less overall coverage, so about 5% less, but that makes sense because some of my cover points are not collecting any coverage. However, I've traded some of the cover points that I know are very easy to hit for some performance, so I can now run more seeds. So that's kind of the game that I'm looking for here. There's loads of other things we can do like this, but that's about it. There's some of the extended tools I mentioned. So what we've got here on the left is what we call the coverage donut, which is a color-coded representation of our entire coverage. I've moused over here a particular cover point, which shows me that it's fully hit and therefore it's green. And it also shows me containers that contain that particular cover points are contained within. I've also got here what we call pivot table. We'll get back to this in our demo to show how that works, but it's quite useful in terms of viewing coverage. So what are some of the hurdles? I'll very quickly glance over this. It's definitely the learning curve, because what we've essentially done is we've implemented a cover point in Python. We actually have some extra infrastructure that adds to that, especially in terms of merging coverage, etc., putting it all in a database, and there's a lot of maintenance to do. And if there's a little gotcha here, as a verification engineer, we've got a typo in that little picture that took off the internet. So what I'll do now is I'll very quickly go into my demo, because I knew I wouldn't have enough time. So hopefully you can still see my screen here. I hope that's the case. I hope I'm still sharing my screen. Okay. Hello, everyone. This is my short demo to go along with the coverage in Python talk. So here's the little spec I showed on the day. So it is written in a XML format I came up with. It could be on IP exact, it could be anything really, as long as it's machine readable. And we're going to leverage this in our coverage definition. And this way, if the architecture were to change, our coverage will change along with it, and so would all our documentation as well. So like we said on the day, we have a little protocol that we've defined. We've called Svet, so I've just used that as the main tag here, and it's got a header, The header's got 4 fields, which together add to 32 bits, and it's also got a payload, which also has 32 bits. 2 of the fields in the header have actually got an enumeration defined here and here. So in our code, we'll actually go and read those enumerations here. So for example, packet type could be write read or some mysterious sync packet. And to see how this is leveraged in coverage definition, if you look here on the right-hand side, we've got some code here to process that XML using XPath expressions, same here as well. So for my first cover point, I will make sure in my motivation, I put as descriptive as possible a message about the cover point, when is coverage collected, what does it signify, etc. So this will also go in my verification plan and documentation at the end of the day after it's all auto-generated. And for each axis, and an axis is really the equivalent of a cover point in system Verilog, and then the full cover point is what's known as a cross in system Verilog. It's just a slight distinction in nomenclature. So we iterate over each field using XPath, so that's just a Python library, quite easy to use. And we add an access for each field where the values are either are defined by this function here, and this function just returns either dict, a Python dictionary using the enumerations in the XML, or it just returns a list of most significant bits given the field size, and that's it. That's our cover point. That's the definition of the cover point itself. So that code here, the one I selected, along with the motivation, shall we say, is all the code we need to define a cover point, produce some documentation, and review it. The execute method, which we'll look at in a second, is necessary for when we actually get around to collecting a cover point. I've also defined a second cover point called payload. It's fairly similar, really. It's got 2 axes this time. Payload, most significant bit, which I've manually defined to be 0 to 32. And it's also got a chip select, which is actually, again, using the enumeration for the chip select field that we've got in our architecture here. So it's using chip 1 and chip 2, just there. That's about it. And I've just stored a little helper variable, so it's more efficient when we go back to actually collecting coverage, called write command, which will just fetch what's the actual value of, the write command. Is it 2? Is it 1? In terms of the header values. And that's about it. And I'll show you how I build this just here. So if I do xg build, this is our little internal build tool. I give it a top of Verif DVClub demo. I say I'm going to use the documentation platform, and I'm going to use a test chip. And that's all I need to do. So hopefully this will build quickly, and it will give me a nice PDF I can go and have a look at, and it will tell me where it is. Okay, so this is done. So let me just copy that location here I've been given. Need to get rid of that space there. And there's my verification plan that I've just built. So I haven't put any text in there, so hopefully that's not too slow. There we go. So that's the documentation I've just generated using that code there on the right-hand side alone. So let's have a look at what's happened here. So I've got a little table here of my cover points that define headers and payload. So this is just a little summary. These are actually hyperlinks for easy navigation, but they do not work in Emacs. So anyway, I'll just skip past that and go to the actual cover points. So this is my header cover point. So essentially this one. And you can see each axis here. It's got either the enumerations that were defined in the protocol spec, or it's got the bit field length. And if we cross this together, 3 times 13 times 2 times 18 gives us 1,400 odd. We have not defined any illegals, so this is just using the define method for illegals for basically saying all the buckets are legal, which is what this default goal here of 10 means. For the second cover point, I've actually defined some don't cares. here. So this is our second point, and this actually gives me the define method that actually specifies those don't cares. I'll just scroll down to show that again. There it is. So what I'm saying is, if the chip select is chip 2, I don't care about collecting that coverage. Otherwise, I care. And that's a really nice feature of doing coverage in Python, is that you can define illegals, buckets, etc., bins programmatically rather than having to enumerate them, which would be the standard way of doing things in System Verilog. I'm aware that we can also do that programmatically in System Verilog, but it's not very neat and not very easy and easily accessible. So that's the documentation. This is how we sort that out. I've also taken the liberty of setting up a little demo where what I do is I issue a bunch of packets, which I just randomly generate. There they are. So each packet is a dictionary with all 4 fields of the header plus a payload. And this is exactly how things would work in an actual simulation. What will happen is the System Verilog will send via the DPI a call to C++, where we have what we call a coverage bridge object, which is just a proprietary library which converts the calls to a Python dictionary and sends it over to Python callbacks. Anyhow, let me just demonstrate how this works and the final results of this. So if I've preempted here, this is my command line. I'm just using a Python wrapper to set up my environmental variables, and I'm just calling this tv.py script, which just takes the generator function I just showed and feeds it into here, into the execute method of this AVP architecture coverage container. So what this shows us is we can actually collect coverage quite easily. So there we are. This is done. It's currently being uploaded to the MySQL database. We've got 5% coverage out of the 100 packets that I just run. What this shows us is we can very easily tune our coverage and our stimulus offline without using a simulator. And then it was quite quick, as you could just see. And I'll just show you the actual results of this. If I go to our SQL database viewer thing, if I select my name here, and there it is. There's my results. So I've got the same script here. Sorry, let me just zoom this because it's probably not easily visible. So there's my log. So the log has also been uploaded to the database. We've got some timestamps. I've got my coverage, and I can actually go look at my coverage here. So I've got that coverage donut I mentioned. The innermost circle is our container, so called architectural verification plan DVClub example coverage model. It's got 5% coverage. If I mouse over here, I've got 2 cover points. One has only got 5% coverage, the other one's got 20, so one of them has done better than the other. I can export this to a PDF format. I can have a look here in the actual table what my coverage looks like. So I've not done very well. So this, if I hover over each of them, I get a nice little preview of how well I've done for each container and each cover point. Same here. So if you can see, we've got a bar chart here giving us for each container and cover point how good we've done in terms of coverage. If I select this cover point here, I can see my don't care cover points here colored in blue. I can see the ones I've partially hit colored in yellow, and I can see the ones I've fully hit colored in green. So I've only got 2 axes here, so it's not particularly interesting. Another interesting feature I can show you is the column collapse here. So I can do that. So basically I collapse this column and I look at this one here alone. Let's look at the other one where we have more axes, and it's probably more interesting. So I've got a lot of coverage to hit here, but potentially some of it might not be particularly interesting. So I might want to focus on some particular things. So what I can do is I can pick up the pivot table view and I can select the axis I'm interested in. So say I want to look at command and address and chip select alone, and this is that coverage, and which just means I'm not particularly interested in the reserved field. And I can move those around anywhere I want. So I can view this coverage any way I wish. And that's my coverage done. I hope that was interesting for everyone.